published Natures in Numbers in 1997. We got a glimpse of the mathematician's view of nature in that book. Ian Stewart's book has many chapters, but today we will focus on Chapter 4, The Constants of Change. If this is your first time to hear about this topic, well, this is the right video for you. Long ago, humans thought that nature swung between two opposing points of view. One believes that the universe obeys fixed immutable laws and that everything is a well-defined objective reality. In contrast, the other believes that there is no such thing as objective reality and that everything is constantly changing. As we uncover the truth about those who shaped this ideology, please lend us your ears and your imagination as we travel back in time. The first viewpoint have shaped science as rights, but still as a society, we see signs that the dominant cultural background is shifting to the second way of thinking. In a few minutes, we will talk about the constants of this reality and how they generate change and alter the class's findings. Now we begin as we step back into the Renaissance with the discoveries of Sir Isaac Newton.
Isaac Newton. When we hear his name, what is the first thing that comes to mind? Is it gravity? An apple falling from a tree? Well, both guesses are correct. However, did you know who Isaac Newton is? Isaac Newton was an English mathematician, physicist, astronomer, theologian, and author known for his law of motion and the law of gravitation. He and his friend Gottfried Wilhelm Leibniz invented calculus and its two techniques, integration and differentiation. Both methods work side by side in one and thus the other. Between them, they tell you that if you know any of the functions, the position, velocity, and acceleration at every instant, then you can work out the other two.
Using the law of physics, the change in nature can be described by mathematical processes. For example, the heat equation is described as the rate of change in the body's temperature. But what is the rate of change? A rate of change is difference between a quantity now and its value instantaneously in the future. Equations of this kind are called differential equations. And with that, we get a callback to calculus. Other examples of differential equations are being applied in real life include explaining exponential growth and decomposition, modification on return on investment over time, and modeling cancer growth or the spread of ABCs.
To learn more about Newton's discoveries, let's take a trip to outer space. Isn't it fascinating how the Earth floats magically in the darkness of space? Who am I kidding? It's not magic. It's the sun's gravity that keeps us in place. A discovery was made over 300 years ago before we even set foot on the moon. The solution of driving the universe in terms of differential equations and then solving it was the basis for Newton's discovery of the law of gravitation. He assumed that the same force must attract all bodies in the universe. The mathematical formula for the motion was solved back then. Some examples include Ohm's law, the law of frictions, and Joule's law. Newton and his successors could not find exact solutions to a system of three or more bodies. Instead, they attempted to devise methods to calculate approximate numbers. For example, around 1860, the French astronomers Charles Eugene Delaunay filed an entire book with a single approximation to the motion of the moon. A simple example of an approximation algorithm is the minimum of vertex cover problem.
Zheng demonstrated in 1994 that a system of three bodies is not integrable. He showed that such a system could exhibit a strange phenomenon known as Arnold diffusion, which Vladimir Arnold first discovered. Arnold diffusion produces an extremely slow, random jump in the relative orbital positions. This jump is not truly random. It is an example of what is now known as chaos, which is defined as simply random behavior with purely deterministic causes. Both the Lorentz attractor and the double pendulum are examples of chaotic behavior. it's worth noting that this approach alters the definition of swift. This word initially meant finding a formula, then find approximate numbers, and lastly, telling how the solutions look like. We are looking for qualitative responses instead of quantitative ones. In some ways, it is wrong to see this development as a retreat. For what this change of meaning has taught us is that for questions like the three-body problem, no formulas can exist.
Overall, Ian Stewart's book Nature's Numbers is filled with helpful information and new perspectives on using mathematics in nature.
Stewart's book expounded the constant of change through differential equation and its relation to change.
Stewart wanted to share with the readers as simply as possible through his book, Nature's Number. He wanted the world to know about Newton's discovery.
Ian Stewart explained that nature relies on mathematical processes and an understanding of nature's pattern using its term and qualitative descriptions.
Furthermore, he advanced it by illustrating how the meaning of the sentence was changed over time by introducing a new constants through the passing of view. With that, we can generally say that constants generate change.